Time travel, the idea of moving through time as easily as we move through space, has fascinated humanity for centuries. It's a concept that bridges science fiction and theoretical physics, ancient mythology, and cutting-edge research. But is it truly possible? Could we one day step into a machine and journey into the distant future, or perhaps even rewrite the past? While it may sound like fantasy, modern physics suggests that under the right conditions, time travel might not just be possible, it might already be happening on cosmic scales. To understand time travel, we first need to dive into Einstein's theory of relativity, which completely transformed our understanding of time. According to general relativity, time is not a fixed, universal constant. It's flexible. It can stretch and compress depending on your speed and proximity to massive objects. This means time can pass at different rates for different people, a concept known as time dilation. In fact, astronauts aboard the International Space Station age slightly slower than people on Earth due to their velocity and weaker gravitational field. It's a small effect, fractions of a second, but it proves that time travel to the future, at least on a minuscule scale, is already real. But what about traveling backward in time? This is where things get even more complicated. Einstein's equations allow for solutions that seem to permit backward time travel, such as closed time-like curves. These are theoretical paths through space-time that loop back on themselves, potentially allowing someone to return to their own past. The challenge? Most of these solutions require exotic matter with negative energy, something that hasn't been proven to exist, but which quantum theory hasn't ruled out either. One of the most popular theoretical shortcuts through time is the wormhole, a tunnel-like structure connecting two distant points in space-time. If such a tunnel could be stabilized, perhaps with that same exotic matter, it might allow for near instantaneous travel between two places, or even two times. Wormholes remain hypothetical, but in 2023, physicists at Caltech developed new simulations using quantum gravity models that suggest wormholes might be mathematically consistent with quantum mechanics. Though still highly speculative, these models are inspiring new generations of physicists to revisit old assumptions. The world of quantum mechanics adds even more layers to the puzzle. In particular, the many worlds interpretation proposes that every quantum event spawns parallel realities, an infinite number of universes where every possibility is played out. This idea, while controversial, raises wild implications for time travel. If every decision creates a new timeline, could traveling to the past simply mean jumping to a parallel world where your actions won't cause paradoxes? In 2024, a study on cosmic radiation patterns hinted that our universe might be subtly interacting with others. Tiny distortions in background radiation that some believe could be signatures of quantum entanglement between universes. It's not proof, but it fuels the tantalizing idea that time and reality might be more malleable than we think. Still, most physicists agree that time paradoxes are the greatest hurdle. The classic example is the grandfather paradox. If you went back in time and prevented your grandfather from meeting your grandmother, would you cease to exist? Some theories suggest the universe would prevent such paradoxes from happening at all, a concept known as the Novikov self-consistency principle. Others argue that paradoxes are avoided because time travel to the past leads not to our timeline, but to an alternate one. In other words, the past can't be changed, only visited. Despite the mind-bending theories, the practical challenges are immense. We would need technology far beyond anything we currently possess: control over black holes, mastery of quantum gravity, and materials that don't even exist yet. And even then, time travel might remain forever theoretical, like a beautiful equation with no engineering solution. But the science is progressing. In recent years, researchers have created time crystals, structures that repeat in time, not just in space, challenging how we define movement through time itself. Experiments in quantum entanglement and nonlinear causality are revealing that our everyday understanding of time may be just a shadow of a deeper truth. In the end, time travel isn't just about machines or paradoxes, it's about how we understand reality itself. Time feels like a river we're swept along, but physics hints it may be a landscape we can navigate, under the right conditions. Whether time travel ever becomes a reality or not, the search itself pushes science forward. It forces us to challenge the boundaries between the possible and the impossible. And maybe, just maybe, the future version of ourselves is already out there, looking back.